started, just want to do a little introduction about AI Camp. So we are a global online platform for developers, engineers, and data scientists to learn and practice AI technology. With the mission of make AI available to all developers, AI Camp have grown over 50,000 tech engineers in the group, have hosted over 300 local tech meetups, workshops, boot camps, large tech conference, and live stream most of the tech talks globally. We have local study groups in major cities in the US, a few cities in Europe, India, China, and Australia. You can take a look at the website to see our upcoming tech talks, workshops, and crash courses that we offer. So we are very excited to have Amir Alush, the co-founder and CTO at Broadman 17. In today's talk, we will learn several important aspects for building deep learning based on computer vision products. So before we get started, just want to give you a little introduction about Amir. As I have said earlier, he was the CTO and co-founder at Broadman 17. A pioneer startup took upon itself to solve deep learning compute on everyday devices. And he have led high professional deep learning research team at Audience and Superfish, which was one of the first companies in Israel to adopt deep learning. So without further ado, let's welcome Amir.
Okay. Hi, everybody. Thank you for attending. Can you hear me well? Okay, great. Okay, so deep learning has gained a huge popularity over the last several years, especially due to its magnificent progress in many domains. Many resources are out there, including open source implementation of recent research advancement. Okay, so this vast availability is somehow misleading, because when one actually wants to create a deep learning based product, he soon realizes that there is a large gap between this open source implementation and a real production grade deep learning product. Closing this gap can take months of work involving large costs, especially of manpower, computer power, and so on. So throughout this talk, I will talk based on my experience leading the research at Broadman 17 about several aspects we have found to be important for building deep learning based computer vision products. A few words about Broadman 17. So the company was founded back in 2016. Today we're a team of 18 plus people, mostly master degrees and PhD in machine learning, deep learning researchers. We're backed by some Israeli venture capital like Lul Ventures, Mani Ventures, and also by Sony Innovation and Samsung Next. We currently focus on developing perception software for ADAS and autonomous driving, okay, which is currently integrated by leading tier 1 and automotive suppliers. The deep learning technology has been engineered from the ground up, okay? So we actually developed our own technique for efficiency, and this is a result of 5 years of research. I'm not going to talk about our research. You can follow us through other resources. Today I'm going to talk about this. So throughout this talk, I'm going to talk about 5 different aspects: the requirements, the data collection, annotation, evaluation metric, and the research. I'll explain each of them, and I will also try to draw the connection between them and see how every step matters, okay? So we are all excited about doing deep learning research these days. So many new exciting methods appear constantly. We have dozens of new papers in archive on a daily basis. So exploring in a free manner of various new techniques and problems may in time actually lead to a new product or become a part of existing product. But it's also highly risky, okay? So I think it's a great advice for any startup or company focusing on AI to always keep such an open research track alive as we do here at Broadman. Today I'm going to focus about the applicative research, okay? So applicative research is the research conducted as part of developing of a product. And as such, the first phase before dealing with anything else should be defining the product requirements. Okay, so these requirements will help define the following steps of data collection, the annotation, and the following research phase. Okay, so the first phase in the requirements to have a clear definition of the task the project is intended to fulfill. You need to define that. We need to define the input data for the AI application, and we also need to have a clear target platform. Where exactly do we want to run on? So these are few steps you should take into consideration when you're talking about the product requirement. And although it sounds very trivial, it's actually very tempting to start just training the neural network or starting collecting the data or annotation before going through this very important step. And that's true especially for startups, which might at the beginning not have a clear product definition, but it's a must from my experience. So let's take a look at an example. So here, I just gave a very mock product for a smart doorbell. It's not a real product, but it might be as well. So the task is actually to give an alert when someone appears at your doorstep. Okay, so there is a camera mounted at your doorstep, and it should give an alert with the 98% recall, with a single false positive per week. The camera should be mounted around 1.5 meters, from 30 centimeters to 1.5 meters from the ground. It should detect full and upper body, and should also assign a unique ID per person. It should actually identify which is in front of the camera. The input is 700p RGB images at 30 frames per second. The camera height, the platform should be a Raspberry Pi, a single core of ARM Cortex A53, and the latency, the time when a person actually appears at your door and the time it takes for the application to alert you, should be around 500 milliseconds. Okay, so once we have these clear requirements, we're set, and we can continue. Let's look at the data, okay, which is the major part of any deep learning-based product and any actually AI startup or company, and let's see how it actually relates to the product requirement. So the first step is talking about the data collection. This is actually the raw data. We later on label or annotate and feed to our learning algorithms, okay? So data collection can be a very long and expensive process. It can be a long process for several reasons. For instance, if you have a proprietary setup like a new camera or a new LiDAR, then you'll need to actually collect all the data from scratch. It's not like you have an existing reference. You have a unique data set. Another factor could be collecting enough variable data, for example, in different location, different seasons, so on. That actually takes time. And even if you rely on another company's data, sometimes internal issue might also prevent you from getting this data very fast. So it's a long process. It's also an expensive process, especially if you need to buy the data, if you need to create your own special setup. For instance, for autonomous vehicles, it actually requires you to build a very unique setup in order to do this data collection. And also, of course, you have to manage this setup. You have to manage all this data collection. So it's very expensive. You have to store and manage these large quantities of data. We're talking about video streams and, of course, other sources of data. So that's actually requires quite a large of operation. So for these reasons, we found our data collection should start early. At the Broadband 17, we started collecting the data from day one, because actually we needed these quantities of data, we needed this variability over time, and we ended up collecting around 100 million images. We had the know-how, we had the resources, so we rushed into it. But you should plan thoughtfully before you actually start this expensive and long process. I can share with you that many of these images we decided to early on collect, we ended up not even using. Because we didn't have a very clear product requirement when we just started, which we only had later on, so they turn out to be not relevant for the specific application. Okay, so you should pay a lot of attention to this, and I'll give you some more examples as we go. So let's talk about data quantity. So how much data do you need? So I think that's the most common and sometimes the only question I hear with respect to training of deep neural networks. So the funny answer is more. But as a startup and even as a big company with limited resources, I think it's not the right question. Of course, collecting an infinite amount of data would be the easiest solution, but it will also cost you a great deal of time and money. You should really focus on the quality of the data, which is more important. And there's a very long and expensive process. We find to be very useful to split the process into phases. So this is kind of a methodology we use over and over. So in the data collection process, you should start with a small subset, just to get a feel of your data, to understand before you fully understand what exactly you need to collect, but start with something small. Don't rush into collecting 100 million images, which will cost you a lot of money and might be not as relevant as you think for your final application. And once you gain confidence, you should increase the pace. And finally, when you get to the research iteration, this will impact the direction of the data collection, okay? And as we'll discuss later on, research experiments and data collection should be jointly managed. So the data collection is not a static thing you do once. It's actually should be something live, like part of your research. Two more things I wanted to touch here. So just putting it here, academic data. So most of us are exploring very many different kinds of academic data, but you should be advised that most of them are not for commercial use. So you'll need to replace them with your own data set, but they're good for experimentation and research just to get a feeling. And what about synthesizing data? So that's a very painful process, but if you know how to do that right, that might be worthwhile to you. I'm not going to touch these two, this point, but just put it here. Okay, so following, let's talk about the data quality. Okay, so we said quantity it's important, but it's not the main issue. The main issue is quality. So let's talk about the quality. So following our product requirements, we should focus on collecting data that is relevant for the product we're building. So, for example, if you have the specific application and the requirements in mind, so you should collect the data that is fitting your modality. For instance, if your product is a camera, is a fisheye, then your data should also be. If your input is infrared, that your data should also be from the same type. The data should also cover the product operating mode distribution. So taking the smart doorbell camera as an example, and let's say we're considering using the Coco dataset, okay? So if you look on so we want to detect people or segment people, it doesn't really matter. So there is a class called person in Coco. So looking at the class distribution of Coco, you can see there are many classes there, including person. But there are also other, perhaps not relevant classes, like different kinds of animals. And I wouldn't expect like an animal showing at your doorstep. So perhaps that's not the best choice of data. And if you zoom in on some example containing persons in Coco and viewing their appearance, it's also very important to know that you need to get familiar with your data. You need to understand the appearance and to understand whether it's actually data that is beneficial for your product. So in Coco, you can see the first image, you can see in the right mirror, you can see that's a person actually. That's also a person. That's also a person on an elephant. That's also fingers. Perhaps the rightmost one is the most relevant one, okay? So even though all of these pictures are labeled as person, of course you understand that only the rightmost one is important. So you should adapt that to your specific application. And it's also true, like sometimes you have legacy data sets you got from your previous project. Sometimes you get data from your clients or your customers or from your from various sources. So even though you have the labels, you should get familiar with the data and understand exactly whether this data actually fits your needs. And sometimes it gets really gentle there. Another example is considering a traffic monitoring application. So you should care about, of course, the appearance of the data, the viewpoint, as well as the modality which acquired these images. So the rightmost images seems to be the best choice here. And even though on the other pictures you also have cars, but again, it's the same example, very similar one. Of course, collecting data with large variability. Okay, so collecting large amount of data is fairly simple, especially in nowadays when we're considering video data. But you get a lot of correlated data there. Okay, so if you consider the smart doorbell camera, then you would expect that using data throughout the day from a single installed camera, it should yield you around 2.5 million frames a day. The data coming from this is static, of course. This is a static environment. The background is almost not changing, and is expected to be highly correlated. Okay, that shouldn't be that data set shouldn't generalize well to other locations in scene, of course. So that's perhaps an extreme example, but it actually emphasizes that the data with variability of various factors like location, time, day, the time of day, seasons, weather conditions, and sources, so on, it's very important. Here is actually a real example of a project we did at Broadman 17. We actually cared a lot about the location, so we worked hard on collecting data from various locations, various sources, and that sounds like a very good choice, like collecting data with high variability. Okay, so we talked about the requirements, we talked about the data collection, and let's say we agree to collect a small amount of the data set and see how it goes from there. Okay, after that, of course, we're coming to the part where we're talking about to actually label the data. So the data annotation is the more expensive and time-consuming part, especially when you consider a more fine, detailed annotation requirements. In this example, you can see semantic segmentation. You can estimate that annotating each of these frames should take several minutes, perhaps even an hour, and considering that the annotator's hourly fee, you could get to several dollars per frame. So that's expensive. So before rushing into annotating millions of these, you should understand exactly what data you should annotate, and second of all, you should understand how to annotate the data. Okay, because the level of details you get to the annotation can affect the cost greatly. Not only the cost, but also the time it will take you. So perhaps you think at the beginning that it's, of course, I need semantic segmentation, and if I go ahead and annotate the data, let's annotate everything very fine grain. Yeah, but perhaps that'd be an overkill, and you'd not get the sufficient enough data or variability, and you pay a lot of money and time getting this data you might not need at all. So you need to choose what data to annotate. Annotating your entire data set is something, of course, not reasonable, especially when all of us have a lot of data. You should actually select the data you think will help you achieve your goals, okay? And that sounds like an impossible task. Like, how do I know exactly how to annotate? How do I know how to annotate? So again, the guiding principle is start simple. Start with an initial subset with preliminary annotation guidelines. Start with something simple, and after you gain confidence, you should annotate more, and it will also allow you to correct your past mistakes. Like, let's say I want to change the annotation scheme, I want to add something else, I want to re-annotate everything. So that's very important. So let's talk about the data quality, okay? The annotation quality. Okay, so the learning approaches, most popular approaches these days, are based on supervised learning. Okay, so unsupervised is very interesting, and there's a lot of research on them, and we all hope they will be mature eventually or even soon. But currently, supervised learning is the most common approach today, meaning that only the data that you annotate, not the data you collect, will be used to train your models. And your models will be good only as the annotated data you feed them with. So if you feed them with too much dirty data, you will hurt their performance. Okay? So before starting your annotation process, what we learned that you should define in the most detailed way you can think of how to annotate the data, and I'll give an example later on. And also, it's important that it's not always something you can get straight from the product requirements. It's actually part of the research. For example, for the application we're considering, the smart doorbell camera, nobody actually defined whether we should develop an object detection algorithm or perhaps semantic segmentation, perhaps image classification. So that actually affects the annotation procedure. Like before, we should start with something. Let's start with let's define an annotation scheme. Let's see if the results are actually good for the KPI, the product requirements has defined, and let's continue from there. And like the data collection, the annotation process is a live process, okay? That's something that should be done simultaneously with the research. So let's consider an example. So let's say we're developing a face recognition application, and it requires face detection as an initial step. So it sounds like a very straightforward. So we need the face detection, but there are many ways you can actually detect, annotate face for the task of object detection. So if you give these tasks for several annotators, each one of them, I promise you, will get perhaps a different interpretation of the task, and even perhaps over time it will change. So not being very consistent in your process can confuse your learning process. Because, for instance, if you include in the background in your object, how will your algorithm will know to separate foreground from background? It will also confuse your annotators, which will not necessarily know what to do. It might also confuse your evaluation matrix. So for detection, for instance, where you consider overlap between ground truth and undetection as something you use for evaluation, if you have inconsistent performance between your algorithm and your data, then you will be punished for no harm, okay? Sometimes other algorithms are depending on the bounding box output for recognition, so that's an initial step. So if you have legacy algorithms trained on a specific with a specific annotation scheme, you should also continue doing that, or at least take it into consideration in your current annotation. And that also happens when you have legacy data sets. You have data set and annotation coming from previous projects or from customers. You should pay attention that the annotation is something that sometimes can be gentle. Okay, so let's talk again about the quality, and also of course affects the cost. So we should find out what exactly we want to annotate, and it goes not only to the details to the level of the image, but also inside the image. So for instance, for a face detection, do we really need to annotate profile faces? Do we really need to annotate far in the back faces, very small faces? Perhaps even if I detect 15 by 15 face, it will not be something useful for a face recognition application. What about this image with all the people? Do I need to annotate the people far in the back? What about the people truncated? How do I annotate them? Do I need to annotate them? So if you decide on the level or exactly how you want to annotate that, that will actually can be very impactful for your annotation process, for your cost, for your accuracy, and so on. So how do I guarantee the quality of my annotation? So there are several ways. Of course, you can use several annotators, okay, and doing some kinds of averaging or so on, but of course that's expensive. So many of the existing third-party annotation services actually use anonymous, non-dedicated annotators. So this actually has the tendency to produce less accurate results because these annotators are less familiar with the task over time, and they tend to have no liability for the task you're doing. So that's actually a factor which is very important. Get to know the people you work with. Also, it helps to keep a tight definition of the annotation task as we described. You can also validate automatically and prune for outliers. And also a very important point here is keep the task for annotation as simple as possible. If it's required, you can pre-process the task. For example, in traffic monitoring cameras scenarios, we found that feeding the different sources in a random manner has a dramatic impact on the annotation quality and throughput. So it should be rather restricting the annotation to similar scenes for the same job, or even break a fine-grained detection into detection followed by classification. So try to keep the annotation task as simple as possible. That will help you to increase the quality and increase the throughput of the task. And of course, because it's a very expensive process, of course, we care about the cost. So other techniques to useful for optimizing the high cost of the process, bootstrapping. So you can use the current algorithms to initiate or clean annotation, okay? You can use temporal information if you consider video streams. You can use any other available information. For example, in autonomous vehicles, you have many different sensors. Perhaps you can build a setup that will help you annotate certain tasks. We can think of that, okay? And that's important because you could also have these sensors only in the data collection step. You don't need them in the actual production step, okay? You just need something that will facilitate your annotation. You can also consider, if you're doing very large-scale annotation, or at least what we found out internally at Broadman 17, that developing an in-house infrastructure for doing that helped us to increase the accuracy from 70% to 90% using our platform instead of a third party, and also reduce the cost by a factor of 6. But that, of course, depends on your specific requirements, on the volumes you're annotating, and of course, you need to put some resources there in order to manage this. That doesn't go. That's not free, of course. So we talked about requirements, data collection, data annotation. So we started to touch the research phase, and before starting with the research, there's one more thing we must do before we can start the research phase, and this is actually define an evaluation metric we would optimize throughout our research experiment. Okay, and that's actually something Andrew Ng has in his some of his online lectures. So that's a very good advice. So there are many ways to evaluate an experiment, many evaluation metrics. Some of them are even conflicting. So you can have true positive rate, you can have false positive rate, you can define average detection rate, you can decide latency as something that I most care about in my application. And improving one metric might be contradicting to improving a different one. So we've noticed that while running thousands of different experiments, that it's not defining the single metric actually lead to a slower or even the inability to reach the product requirement. For example, when different researchers find subjectively different matrices to be more interesting or promising to pursue, rather than choosing the metric that actually satisfied the requirements we're trying to meet. So on the rightmost, on this figure, on the rightmost figure, you can see a kind of a process while not defining a single evaluation metric. You can imagine how this procedure actually leads to contradicting results, and by that you might not meet your product requirements, and even if you do, it might take you a very long time. And on the left, you can see our hypothesis that's saying that if you have a clear goal, a clear target, that will help you get much faster and a much more efficient way to your goal. Okay, so I'll cover that later on. So let's go over the initial example I gave with respect to these 4 steps. So we have the product requirements, that's defined. We decide on the data collection. So a reasonable choice would be, let's collect only 720p RGB videos, 1.5 meters high. That's the setup. 20% of the data is going to contain no objects, while 80% is going to contain objects. And then sounds like reasonable, because most of the no object scenes are pretty similar. So we don't want too much of them. And the interesting information is in the videos with objects. The data annotation should be objects, so data bounding boxes, only full body and upper body. We don't need far away objects. Let's say we decide to annotate 5% full videos and 95% sample videos. And the evaluation metric should be the recall as defined, with the constraint of 1 false positive per week, and the latency should be less than 500 milliseconds. And that's important because if you start with a very big model that will not hit these requirements, not even with the hard work, you shouldn't actually explore these. That would be very wasteful. So only after we defined our data collection strategy, annotation, and optimization metric, we can start the actual experiments. Okay, so that's what we want to do as researchers. And you can view applied research as an empirical process, iteratively, constantly improving the evaluation metric by following 3 phases. Phase number 1 are the research experiments, followed by an error analysis phase. We want to actually analyze what we've done so far. And then, of course, the live data collection and annotation should be done constantly. So the research phase, or the research experiments phase, involves training and evaluating many different hypotheses, many different neural networks, exploring different architectures and algorithms, learning hyperparameters, data preprocessing, augmentation, and so on. We all know that very well. So that's a steady state step. And in the analysis phase, we measure the model's performance using the chosen single evaluation metric. Okay, so by following the standard good practice of splitting the data into training, validation, and test, we can actually estimate what is the current status. And since we're using a single evaluation metric, we can actually analyze the network performance with respect to these metrics. You can see on the table of the left, by prioritizing the different factors in our models, algorithms, data processing, data annotation, data distribution, etc., and computing the impact on the evaluation metric we optimize for. So in this example, you can see in the first row, so the number 1 priority is wrong annotation. So wrong annotation actually accounts for 25% of our error. And closed objects are 20% of our error. Truncated objects 3%, and people holding umbrellas, which we missed, we don't detect, amounts for only 1%. Okay, so actually prioritizing keep us focused on dealing with the factors which are most critical to our product release, and not defocusing by subjectively prioritizing. For example, one might find that solving for the people with umbrellas might be the most interesting task because he already has a solution. Sounds like the best data, but actually that's not something that will take you very far in your next iteration. So it's very common, actually, we've noticed that not assessing empirically might lead to a subjective bias of what should be solved next, hence making the time to product longer and wasting much more resources and time. And of course, throughout the process, you should evaluate the data. The data is an integral part of the research. It's not something you do once at the beginning. So considering the different factors in our analysis phase, so we might think that additional data collection and annotation for our weak points. For example, if we're developing an ADAS application, perhaps collecting more car accidents data would improve our next phase of research, okay? And that's something we could not actually predict when we just started doing that. Okay, we only know that as we go along. Cleaning our data annotation, perhaps we have a mislabeled data and actually affects our performance, so let's clean that. We can also change the annotation scheme. For example, if we've noticed that we can't meet the requirements by training using 2D rectangles, perhaps we should go to a more expensive scheme and annotate 3D boxes. Perhaps that will solve our problem. In the image with the faces, perhaps we're very bad at small faces, and that's part of our requirements. So let's annotate more small faces because we are not as strong as we'd like to be. And all that, when we follow these 3 steps, it should, from iteration to iteration, with clean data or additional data and improved algorithms, everything should improve are a single evaluation metric and take us further, okay? So these research iterations, we found out that in many cases, it takes many of these iterations in order to meet the requirements. So the research iterations are very demanding in terms of researchers, compute resources, and time. So we naturally at Broadman 17, we wanted to optimize for this, especially to increase the researchers' productivity and letting them focus on what they do best, which is research. Okay, and also, of course, reducing costs and so on, especially with these very expensive GPUs involved in the training of neural networks. So the main thing a researcher had to do is to develop new algorithms and optimize current ones. So I think that's what we're interested at, okay? But there is a lot of overhead, especially in the era of deep learning and very large data sets and compute environment. So we need to set up a compute environment. We need to manage all the data, annotation, sorting, preparation, fetching the data to the machine. We need to monitor periodically and check if everything is going well and so on. And sometimes that's very hard because these processes, training processes can take even weeks, okay? If you actually build a complicated pipeline, at Broadman 17, we have a very complicated pipeline of algorithms, that's actually very difficult to do this bookkeeping of what goes next and so on. And you might lose a lot of time unless you start to automate it. And that the problem gets even worse, okay? So as we grew and we added researchers and the projects, of course, are getting more and more projects and so on, we noticed that it's actually not scalable. It's not something we can do manually. Considering hundreds of experiments, you actually need to run simultaneously, okay? It's a process, it's error prone, it's not efficient in terms of resources. It's actually not doable. So we actually decided to build our own training platform. We call it Cortex, in order to keep these iterations tidy and efficient. So some of the design principles that were important to us were a platform that actually is able to share resources, orchestrate the training of the different models, versioning of everything. You want to know which data you will use to which model, and you want to be able to reproduce this. You have to monitor everything. And also you want to allow to build complicated pipeline, okay? So, so I've covered several topics going from the requirements, the data collection, the annotation, the research evaluation metric, and the research. And I hope I was able to explain in a good way of how all these steps are actually related, because there is a tendency to neglect most of the steps except for the research phase. But that's actually, from my experience, it's very important to pay attention to all of that, and also keeping them alive simultaneously. So thank you very much. We are located in Israel. If you're passionate about AI and you want to explore more, please visit our website. And I'm open, of course, for questions. So I'll be happy to answer everything I can.
Thank you, Amir. Thank you for your speech. And now it's the Q&A time. You guys can leave your questions in the chat, and then Amir will be happy to answer for you guys. I think there's already some questions down there.
Okay, let's. Okay, so let's see. Okay, so let's answer the first one. So which tools are you using for the data annotation? So for the data annotation, there are many tools out there. So we actually we built our own tools for internal annotation, but there are many open source tools out there. Some of them are actually pretty good. And of course, if you're using a third-party data annotation provider, he will be able to let you use his tool. But a lot of that actually depends on what your specific requirements are. So if you have very specific requirements, of course, you would need different tools. Okay. Okay, so how do you feel about custom matrices? For example, optimizing for metric X without going below value Y for metric Z. Okay, so actually, that's something that makes a lot of sense. So for instance, in our example, we care about, at Broadman 17, we care about deploying these neural networks on very tightly, very tight hardware, meaning with not many resources in terms of compute and memory, but also in high-end platform. So of course, for all of these, we take into consideration what are the requirements. And as I mentioned in the doorbell camera example, if you have a constraint that the model has to run with a specific latency, in that example it was less than 500 milliseconds, so that should be actually a constraint to your training, but you can play with exactly when you introduce these constraints. So that actually gives you a bit of a flexibility. But as I mentioned, if you start with a model that is very far away from this constraint, don't be surprised that when you get to the time you need to deploy that, you'll find out that you wasted a lot of time, and now you actually need to go and do something else. And that should be wasteful. So that's good, adding these constraints, and we find ourselves, of course, developing in that way. Of course, we have the privilege that our technologies allows us to a lot of flexibility. Okay, can you please get back to the part where you spoke about what to annotate? Okay, so I can repeat that orally. So basically, talking about what to annotate, that's actually, as I mentioned, it's important to understand what to annotate in two levels. The first level, the higher level, is the what images you want to annotate. And the second level is inside each image, how exactly do you want to annotate? So I gave some examples there, for instance, for face recognition application. So let's say your algorithm actually is able to recognize frontal faces. So you actually shouldn't annotate profile faces, even though you can. So let's start with the things you clearly know exactly what to do. If you want to detect persons, so I gave an extreme example of a highly crowded scene. So if you give to a human annotator the task of annotating every person, it might take him a very long time. But it might turn out that your algorithm actually is not able to even learn these very difficult use cases, or most important, you're not interested in actually in the person application annotating for fingernails or highly obstructed. So you need to define everything very tightly, and as tight as you can, because that will be very efficient in terms of time and money. Okay, next one. Okay, so what's an example of a good third-party dedicated infrastructure management system for research management experiment? So I guess you can like your current experiments, what is the status, and so on. They give you like a nice TensorBoard overflow. Some of them even gives you the ability to launch experiments very efficiently, let's say on Amazon, on AWS, on Spot instances, and so on. So it actually depends on requirements, because we internally, because we have a very complicated pipeline, which I can't go into details, we didn't find these tools for our needs very helpful. They were helpful, but the core essence of what we're trying to do, we had to write it from scratch, and all the extra effort was actually pretty easy once you do all that. But you can Google that. You can find, there is an Israeli company. It's actually powered by Samsung Next. It's called the Missing Link AI. So I presume you'd want to check their website to see if it actually helps you. Okay. Another question. As for deep learning, what advantages PyTorch over Keras in the job market? Okay. We find we've explored various flavors of platforms, and we do the separation between the research phase and the production or the deployment phase. So we do a complete separation. So in the research, developing the networks, training them, and so on, we care, and of course, all of you should care about the flexibility it allows you. The researchers should be like the environment should be transparent to them. So PyTorch is an excellent environment, and we find ourselves adopting it very fast and very warmly. For production, if you want to actually deploy your algorithm, so we actually went ahead and we've written our own inference engine. But even if you don't have your own inference engine, I think you should pay attention that you have other considerations in the development phase and in the production phase. And for research, PyTorch, and I hear it all around, PyTorch is an excellent environment. You should focus on PyTorch, in my opinion. Okay, so do you have a protocol defined process for understanding your algorithm's mistakes and taking them into account and adjusting and improving? Yes. So the error analysis and the way to get feedback to the algorithm should be understood by you, and you should be able to take this feedback and feed it to your next iteration of research. Because if you don't do that, then you can think then you might think that you're wasting your time here. Okay, so you spend a lot of time, a lot of money on doing these iterations, especially time, and if you don't have if you don't do the analysis, if you don't understand exactly what went on in this step, why we improved, why we didn't improve, and understand exactly what's going on, you're actually going to the next step without understanding where you are currently. So nothing actually guarantees that in your next step your state is going to be better. So sometimes it's good to just stop, analyze everything, and just then move forward. So and it's very easy to just run, do these experiments, run more and more and more and more, and that's actually very addicting. So especially for researchers, okay. But you should stop and analyze and just then and do that. Of course, you can put a threshold there exactly on how often you want to do that, but we found it doing it as often as possible, it gets us the best results. Okay, so Amir, why are your company's solution is better than other schemes such as YOLO v3 and many others? Yeah, okay, so basically at Broadman we developed, so YOLO v3 and many other open source architectures are basically developed for, these are excellent algorithms, excellent architectures, and I have nothing, I've only good things to say about them. They were developed for academic purposes, basically, most of these. And at Broadman 17, what we did, we don't rely on these open source implementation. We actually, when we started doing that, the focus was we care about the real products. We care about getting these algorithms running into production, but we care about the runtime and we care about the accuracy. And that's a very strong goal you set to yourself when you start developing that. And that actually enforced us to think very creatively on how exactly we want to do that, and with a specific set of mind that we want this to go into production. And I'm not sure that many of these open sources out there are in this state of mind, and they shouldn't. Actually, they shouldn't. They should be for academic purposes. Okay, the fact that they are being used for commercial purposes, that's the way things are today because of the rapid movement. Everything is going so fast, And also, it's very easy to just take an open source implementation and try it, and even sometimes put it in your product. Okay, so we're actually because we started having from scratch, it actually and with a state of mind that we want this to go into production, and we were willing to pay the price of doing everything from scratch and investing all these years. That actually gives us a big advantage over these open source implementation. Okay. Yeah, concerning performance and so on, so these are stuff we release over time, and usually it requires signing an NDA and so on. We give it to many of our partners, of course, investors and so on. The gain over open source implementation by keeping the same accuracy is orders of magnitude. Many use cases, Broadman 17 algorithms, we are able to run in a very tight, constrained environments, like a few watts power consumption, very tight memory consumption. Sometimes even classical algorithms, like classical computer vision, cannot run them, and we are able to run our state-of-the-art algorithms there. So over time, we will share more results to the communities. But I do encourage you, you have our GitHub. We have a GitHub repository which we've published a few months back. We have there actually an open source, not an open source, but an open implementation. We have a library running on several processors, including ARM processors and Intel CPUs. You can check out one model we've released, which is a face detection. So you can check out current performance and see how it goes. It's pretty amazing.